I'm Turwal. I'm here today to talk about high-performance production databases running on Ceph. And I'm an architect at Medallia. Medallia, for those of you who don't know us, we collect, we analyze, we display terabytes of structured and unstructured data for our multi-billion dollar clients, and we do all of this in real time. Now, I've been here since 2010. We've grown from 70 to 700 employees. And the reason I'm here today is we actually run real live high-performance databases in production with customer data on Ceph. Now, our journey there has actually been a little bit of a long one. Started about a year ago. We have an in-house analytics engine, which is really high performance. And we had a new version of it, which was even higher performance, scaled to thousands of servers. And then we took a peek at our production environment, which was hundreds of servers, not thousands. And all of these servers had individual names, and they were all of them individual, tiny little precious snowflakes. They were all entirely different. All of the services that were running there were manually placed somewhere, and so was the server placement. It literally was, there seems to be space in this rack, therefore this is where the server goes. There's no connectivity on the switch, but there's connectivity in the switch over there, so let's have a long cable. This quickly ended up with all of the snowflakes in an environment where the mantra goes, don't touch it. And the most precious thing we had was the database servers. They were really, don't touch it. Don't upgrade the BIOS. Don't upgrade the firmware. If there's a critical bug fix for the storage controller, well, upgrading it will imply downtime. And there's a possibility that with this critical bug fix also comes a new bug. So do you really, really need to fix a bug fix that may or may not cause storage corruption? So it was clear we needed to do something. In fact, we needed to do quite a lot of something. So we said, okay, instead of incrementally going step by step by step, we're going to actually jump directly into the future. I'm going to skip ahead 2 or 3 generations and go directly to next generation. That means we looked at microservices, we looked at containers, we looked at, well, pretty much every industry buzzword that is out there. We did set up a proof of concept. Our proof of concept uses 40 gigabit networking end-to-end all the way down to the server. It's non-blocking, it's open networking. We use Ceph for the storage layer, and we use Docker for the containerization. And this proof of concept really, really blew us away. We did have to modify Docker and the networking and Ceph a little bit to get to the level we wanted. But at the end, it's resilient enough that it's actually a major problem for us to test the resiliency. We have to kill so many servers to get to the point that this does not survive that we actually run out of capacity before we run out of resiliency. And it was also extremely performant. In fact, it was performant enough that it was on par with our current dedicated database servers. And these are purpose-built beasts to run databases as fast as they can. Now, when the raw performance is at that level and the resilience is at that level, the question becomes, can you run everything we have on this new infrastructure? Now, to do that, we actually went and said, okay, we're going to need some design goals here. First of all, we want commodity products. It means we want commodity components and we want supported open standards. We really like things where we can go look at the source code. While it doesn't always allow us to actually fix issues, it gives us the illusion that we can. It gives us this sense of control. And it does give us a little bit of an insight into what this company or provider actually thinks about quality of code. We want fully automated provisioning and reinstalls. We want things that are cheap and scalable. And when I say cheap here, that doesn't mean I want to spend less money, but it does mean that I want more compute power, more storage capacity, more performance, more networking for every single dollar that I spend. And we want it to be scalable. We really want something where if we need more capacity, if we need more performance, if we need more of anything, we just add more racks to it. Lastly, we want immutable servers, and that really goes towards once the server is up and it's serving traffic for some kind, it shouldn't change. If you've ever done production level debugging and figured out that somebody has upgraded the JVM, but the JVM that was running when this application was started was a different version, these are not so fun to debug. We also very much wanted a case where there are no special machines, no magic appliance sitting in the corner, no little thing that's sitting over there that everybody knows is essential, but nobody really knows what it does. All of those have to go. We shouldn't be a single service that is tied to specific hardware. That means every component must be able to run anywhere. As much as possible, we run redundancy at the app layer, at the software layer, instead of having individual servers with double power supplies, double networking, more layers of RAID than you really care to think about. These things will inevitably sooner or later fail, regardless of how many cables you've actually pushed into the box. So if you design for failure, think that it is going to fail sooner or later. So we'll design around the failure. We design for self-healing, we design for resiliency. You end up with something that is ultimately much, much easier to maintain. The most important principle, though, is keep it simple. Because if your design for your entire infrastructure is simple, then it's also simple to fix. It's simple to diagnose. It's simple to understand. If somebody new joins your organization, it's simple to explain to them how everything works so that they will be productive in a very short time. And you no longer have the case where when something breaks, everybody is looking to a consultant to go fix it for you because nobody actually understands it because it is complex. And mostly simple means that in a short presentation here, I could actually explain the major design goals and the major components of how it works, and hopefully to a level that someone else can go replicate it. Now, we ended up with a standard rack. Our standard rack is 22 compute nodes. The compute nodes are Intel CPUs running Linux with memory, 40 gigabit networking, and a small SSD. This SSD here is used mostly for the components and or the containers and the boot OS. Our storage nodes are also Linux with an Intel CPU, some memory, same 40 gigabit networking, a lot more storage necessarily, and PCIe NVRAM for journals. The NVRAM for journals is being rolled out right now, actually as we speak. So by the end of the day or tomorrow, we should have that up and running. One of the great advantages of Ceph, you can do on-the-fly updates. I love it. And our networking, we have 3 switches per rack. This is also Linux with Cumulus, and it's also Intel. Granted, it's a lot less powerful CPU, but it has the same amount, it has the same concept of binaries, portable across all of them. It has memory, and it has a lot more networking. In fact, if you log into the switches here, they look like any other server. They just happen to have 32 network cards. So this is unified and scalable. And what this means for us is that my monitoring tools, things like how do I look for host health, that's the same tool on my compute node, my storage node, and my networking switches. Now the challenge is, if you're running everything as container, is really where do you draw the line? You can run your application in a relocatable container, and in fact, that's been done quite a lot. You can run your load balancer in a relocatable container. That has been done, but it's a little bit more challenging. You can run your DNS server in a relocatable container. That actually turns out to be quite challenging. And finally, you can run your database in relocatable containers. Running the database in relocatable containers is a major problem because the database sort of requires resilient storage, and it really wants the storage to be the same after a power loss. Also, unlike my application talks to Zookeeper. It has no problem doing dynamic discovery. My database, Postgres, has no concept of what Zookeeper is. It talks IP addresses. So there are some challenges that we need to overcome. The first one is networking. Let's follow the life of a web request. Web request comes in, talks to the data center firewall. Our firewall forwards this to the host where it's been told that the load balancer is running, in this case Nginx. Now our Nginx modified to go talk to the Zookeeper, and it knows where the Zookeeper is. In Zookeeper, there's information of here is the application for this URL. This is forwarded. Now at some point in the past, the application talked to the Zookeeper. With this basic setup, which you can just get off the shelf almost anywhere, your application can be relocated anywhere because it doesn't really matter what the IP address for it is. It's going to talk to the Zookeeper to update itself when it boots. But what when these 2 servers dies? Well, if the Nginx host dies and we need to start Nginx somewhere else, and we need to give it a new IP address, then we need automation for updating the data center firewall. Generally speaking, having automation that updates your firewall from the data center network itself is not really something your security group is going to enjoy. And for the Zookeeper, how do you actually find the Zookeeper if you don't use the IP addresses? If the Zookeeper's changed IP address? Well, Zookeeper does have quorums. You have 5 of them. But sooner or later, if you just wait long enough, you will have lost more than 2. So you can say that I find Zookeeper through DNS. Well, in that case, all you've managed to do is make DNS that service that cannot fail and that needs to be relocated. So we've modified the standard container networking, specifically for Docker, to use full layer 3 routes to every single container. What that means for us is that every single container has a unique IP address and is visible across the entire data center. to do this propagation of IP addresses, which you need in order for us to figure out where is the IP address located now, we use OSPF. You could also use BGP. We just picked OSPF because it is fantastically easy to set up. OSPF is a linked state database. It's supported by every vendor. And this support by multiple vendors is important for us in all the components we look at. For OSPF, we looked at all the major storage providers, network providers, and quite a few of the white box providers, and all of them, every single one has a working OSPF implementation, and we were not able to find a pair of two vendors that were not compatible in their implementation. So this means it's very easy for us to switch to any other provider if we so wanted to. And this does give us fully relocatable IP addresses. Now, let's say that I'm not talking about a web application, I'm talking about a Postgres database. Well, let's say that we're running this, the application is talking to Postgres, and the server dies. That's unfortunate. But hey, I can relocate the Postgres database instance, and it maintains the same IP address, so the application will be able to connect to it real soon. There's only one small problem, which is that the storage it was using is still on the host that is now dead. This is where we went to Ceph, because the problem here is Docker images are ephemeral. They have persistent volumes, which work great on your local machine. There are a lot of solutions, both proprietary and open source, for Docker volumes to be relocated. But if you want something that is actually full-on high availability, in other words, it will survive not just a voluntary shutdown, but oops, the power went out, you have to go look at iSCSI, which you have to go talk to a large storage vendor, which sells you an appliance, and they're very happy because the large storage vendor earns a lot of money on this appliance. You can talk to the same large storage vendor and say, I want NFS because I want something that is a little bit more file system-like. Great. The large storage vendor is now super happy because this is even more expensive and even less performant. Or you can try PNFS, which seems to be the direction that the storage vendor industry wants to go. We tried PNFS. It did work for a very short amount of time, and then it really didn't work anymore. And most of these proprietary solutions are scale up. If you want to do scale out for them, it really ends up being you buy multiple appliances and you say, these file systems are here, these file systems are over there. The really major one, though, for us was the SLA. All of these large vendors, they support 4-hour hardware support on site. They will have a tech on site in 4 hours to tell you that you have a problem. You already knew you had a problem. And if you have a customer on the phone, and this customer is telling you, hey, I'm paying you a lot of money, where is my data? I can't access my application right now. 4-hour hardware support isn't good enough. You need something that is simple enough, easy enough to go fix, diagnose, repair, that your own people in-house can go fix it in a matter of minutes, not hours. So this being the Ceph Tech Talks, I'm not going to go too deep into how Ceph works. The important part for us is that there's no need to communicate with a metadata service in the hot path. It truly is a scale-out solution. It is also a very, very clean design. There's a white paper for how Ceph works. I recommend you go read it, because reading that, this was easy enough for us to understand that we can go fix some of the basic problems ourselves. And it gives us the confidence that in the future, if there is a problem, we can actually go fix it. And there's a large enough community that will make sure that the problem doesn't appear again. And it is, if you need more capacity, you just add more servers. If you need more aggregate performance, you just add more servers. If you need more single node performance, as in single client performance, that's where you have to get a little bit creative, and that's what I'm going to get into here. But with this, the storage problem is solved, because if my Postgres host now dies, I will just start the server somewhere else. It's connected to the same replicated cluster. It has the same IP address. To the application, this looks like a temporary network glitch, at which point it reconnected to the Postgres database, and everything's now fine. Now, if you have relocatable infrastructure, you can actually have these two piggyback on each other. Because what happens when a server for your Ceph monitor dies? It's an interesting task to switch the Ceph monitor IPs. Technically speaking, you can add a single monitor, remove a single monitor, add a single monitor, remove a single monitor. It is a little bit not giving me warm, fuzzy feelings when I do it. And also there's a problem, which is if you don't update the client config, then if one of them restart in the middle of this, they will try to connect to the monitors that no longer exist. But hey, the monitors are services. There's no difference between a monitor and a service. So we set up the monitors, and each of them get a unique IP. If the machine that hosting the monitor dies, we just start the same monitor somewhere else with the same IP. At that point, the monitor is going to come up, conclude that it is very out of date. In fact, it has no data whatsoever, so it will happily clone the data from the other monitors, and then it's up and running. Now, this is not automated. The foobar potential here is very high because if you have a split brain scenario, or if the system decides that the server that was running the monitor is dead, but it turns out it actually isn't, now you have two monitors with the same ID, and hilarity ensues. So far, this is a task where the human being must be able to go in and say, yes, the server is really dead. Yes, really started somewhere else. But it does give us relocatable monitors. There's human intervention, but no human has to go to the data center. And with this setup, we are really in a space where for our servers, if a physical server dies, and it doesn't matter which server it is, or if a physical switch dies, it doesn't matter which switch it is, well, it's a problem to be solved next week. We just mark the server as down, and once a month, we have our hardware vendor come on site with spare parts, fix the servers that are broken, and go again. There's no point doing this middle of the night rushing to the data center to fix your physical server. Now, for provisioning and orchestration, this is a twofold item. The first part is we always network boot our servers, both the storage servers and the compute servers. We have a small pre-OS, Linux and IntraMFS, which is actually the Ubuntu Net installer with a few small modifications and extensions. We use this to do self-encrypting drives. We have data at rest encryption for everything, including all the compute nodes, the boot drives. So the key is never known by the runtime OS. And this literally means that when the server powers on, it cannot boot because the boot drive is encrypted and the server doesn't have the key. It has to network boot to get the key. Now, what this gives us is, first of all, it means we meet certain data at rest encryption requirements. More importantly, it means that if I have a problem with the server, it is actually completely safe to unrack that server and toss it in the trash because all the data is encrypted. There's no way to get it out. Other things the remote booter does is check the state. If told to do so, it will go and update the firmware, check the BIOS version, check the BIOS config, and make sure that the OS is the right release level. And when all these are done, it will go boot the OS. Now, this firmware and BIOS and version and config is actually really, really important when you talk high performance. In most distributed systems, performance is not dominated by the fastest machine, it's dominated by the slowest machine. And it's very annoying to figure out that out of your 64 storage nodes, one of them happened to be running an older version of the storage firmware and is actually slowing everything down across the network. So doing this gives us completely uniform machines. We don't have any half-installed, half-forgotten state. All of them are always completely identical. And for us, it means that when we do performance improvements, we do it on one machine. And once that one machine looks good, we say, this is the new golden state. Please clone it to everybody else, including firmware settings. For orchestration, we use Aurora and Mesos. Aurora is programming against your data center like it's a pool of resources. And it's fairly straightforward. Mesos keeps track of your data center. In other words, it keeps track of where do you have spare capacity, how much capacity is there. There's a lot of different schedulers, one of which is Aurora. And for Aurora, you will tell it, I want to run this particular job, I need this many CPU cores, I need this much memory, and I want this many instances. You can also give it fairly complex rules, such as, well, much like the Ceph resiliency rules. You can say, hey, I want 3 instances, and I want them to be in different racks. For us, this is really important because we stripped down our servers as far as we could, so they run single power supply, single networking, and we have resilience at higher levels. So our failure domain is 1 rack. So when we run 3 instances of something, it is important for us that they run in different racks. We did have to extend Docker a little bit, specifically for the ability to give it this unique IP and tell it use layer 3 routing, stay out of netting, no layer 2 bridging. And we also have modified Docker to directly mount Ceph volumes. So this will do behind the scenes the RBD map. If the device you're looking for, like in this case, if there is no RBD for demo, it will create one. Since the images are thinly provisioned, our default size for everything is 10 terabytes. That may come back and haunt me at some point. It will then run, MKFS and mount it if needed. If it's already there, it's just mounted with discard options. And in this case, it we're telling it specifically this is a Ceph volume, and it wanted to read write. And this is all it takes to actually get up a fully relocatable thing. If I run this, were to do some modifications inside this demo, shut down the server, run it somewhere else, I would actually get the same data. How fast is it? That's where things get interesting. On the networking side, we get about 5 microsecond latency with the super high-tech performance tool called ping. In reality, the latency can be lower if you run full-on RDMA, but 5 microseconds is small enough that I don't really care. For our application, a lot of that, unfortunately, is still dominated by single-stream TCP. The performance for single-stream TCP is either 22 or 38 gigabits per second. I'll get back to why in one slide. For multi-stream TCP, it maxes out at close to 40 gigabits, and we can relocate IP addresses across the entire thing in less than 50 milliseconds. In other words, if an IP address was on one end of the data center and then needs to be moved to the other, that takes less than 50 milliseconds. For storage, single-stream I/O is 550 megabytes per second. That's completely limited by the SATA SSDs that are run on the storage nodes. If you have multi-stream I/O, in other words, if you do a lot of I/O across multiple RBD images at the same time, we can get close to 4 gigabytes per second. And we can reattach in less than 50 milliseconds. In reality, I think the relocate and reattach time is a little bit less, but this was the granularity for my timer on the test I did. Now, the reason that performance is so varying for the network is NUMA. Now, think of a storage node. On a dual socket system, you typically have two CPUs, two physical CPUs. Each of them have local memory, and each of them have a local PCI Express bus. And the problems really start to appear if you have your network card on one CPU connected to the PCI Express bus, and the SAS or SATA controller on the other CPU connected to that one's PCI Express controller. Because for a single request, imagine that all we want to do is copy data from the SATA or SAS controller to the network card. Let's assume that the thread that wants to do this work actually runs on CPU 0. When it wants to talk to the SAS or SATA controller, it has to go over this inter-CPU link, take control of the necessary resources, do the remote I/O, and every single command or port change it wants to send to the controller has to go over this inter-CPU bus. When it talks to the NIC, it is really fast because it's local. This turns into be a little bit of a performance bottleneck. And you have the exact same problem if your task runs on CPU number 1. Now, talking to the storage controller is really fast, but a NIC is slow. If you are on lower speed grade networking or lower speed grade SAS SATA controllers, then this bus is not a problem at all. But the second you really, really care about latency, really care about single stream performance, it is a problem. Now, we have solved that on our storage controller by running single socket. So all of them run single socket, which means both the SATA controller and the NIC and everything else is attached to that single socket CPU. There is no NUMA, there is no bus. That is the bottleneck. This does, of course, limit the number of cores you can have per storage node. Today, we run a 2667 CPUs. That's 8 cores at a little bit above 3 gigahertz, which, as it turns out, is complete overkill for an OSD node. Demo time. So I do apologize. I had to record this demo in advance. Being connected to the VPN and on BlueJeans at the same time turned out to be a little bit of a challenge. So let me open this. So this is my demo. The URL here, by the way, should be live, so you can actually go and look at the URL, though that's going to show the end state. So this is a small application. This is written in Node.js. I do apologize. This is my first Node.js application ever, so there's probably quite a lot of style things that are wrong here. But it does connect to a database. It does a little bit of a select, and it just shows this on the screen. Now, if I have a client and I connect to this database, I can insert values to it. Everything's looking good. I can load it up, and yes, it's there. It's actually a database. Great. Now, if I go look at where is this database running? So on my Mesos, I can figure out that, okay, it's running on this particular host right now. So I can, let's see here now, shell into that host. And how do we actually demo that something is resilient? Well, you can be nice to it and you can say, please shut down the database, all of that, or we can actually be nasty to the host itself. Just double checking that you do the right host. I once rebooted the wrong host That was not fun. And let's see here now then, and it is gone. So we just powered off the host that was running the database. Now, how does this look to the application? Well, the database is now gone. Where is it? Well, to the client, it looks like somebody rebooted or restarted the Postgres server. In reality, it has now been relocated to a different host, gets the same IP, connected to the same storage, and our insert statements work, and the application is still responsive. So let's talk performance, and let's talk specifically real-world performance, because real-world performance and what you can read on data sheets are two very different things, especially when it comes to databases. On the data sheet, you will see that an SSD has 100K 4K random write IOPS. Fantastic, great. That is absolutely true if you have a very deep IO pipeline and you never need to acknowledge the writes. In the real world, databases work differently. They don't have an IO depth of 64, they have an IO depth of 1, because they will usually read an index, then it will, okay, what is actually in this index block? And if it's a B tree, well, it could be several layers of index, so it's read index block, process index block, seek, read index blocks, process index block, seek. And it's this iterative process of, please give me one piece of data, process it, and then give me the next piece of data, which means it actually is a random pattern where it processes in between, so you need a full round trip. More important, though, is writes, because a database, well, when you write a transaction, especially when you write this word known as commit, the guarantee to the user is that this is now persisted on durable storage. In other words, if somebody were to pull the power on absolutely every single thing in the data center right this nanosecond, it will survive and be there when you get back up. This means that a transaction commit is a full round trip all the way down to the storage layer to be able to say for sure that, yes, this is durably stored. Now, in the real world, a dedicated database server has a lot of buffer cache. If you just, and these prices are just taken from Newegg, but 800 gigabyte entry-level enterprise SSD with supercaps, if you buy 24 of them, that's 15K worth of hardware. 512 gigabyte of LPDDR DDR4 RAM is 4K. So yes, dedicated database servers have a lot of buffer cache. Now, for us, we have two types of tables. We have a few gigabyte tables, and we have a few terabyte tables. Our application does very, very, very heavy caching, so there are few read requests. And even for the few read requests that are there, well, if you have a database container, or if you have a dedicated database, but we'll stick with the database container, they have plenty of memory. So most of the indexes and most of the small tables, they actually sit completely in buffer cache. So your read performance is dominated by how fast you can read from the buffer cache, loosely translated, how fast is your memory. And the memory is fast. But if a user actually modifies something, then there's a transaction, which means our bottleneck is around fdatasync, especially if there are multiple users with multiple transactions at the same time, because as long as the transaction is running, it still holds locks. So it's really important that this fdatasync returns quickly so that the locks the transaction holds can be released so that the other transactions can start grabbing them. Now, if you look at Ceph, specifically RBD, there are three ways to mount it. You can mount it with Fuse, which is easy and gives you slow performance. Quick FiOS with mixed read-write with fdatasync gives you about 640 IOPS. You can also use the iSCSI target, which actually is a lot harder to use, and it's slow, and has a mixed read-write I/O on par with what Fuse does. And then there's KRBD, which is the in-kernel RBD. It's actually really easy to use. This is RBD map, and it's a lot faster. In the same mixed read-write test that I did for the other two here, it ended up with 1550 IOPS per job. The downside of the in-kernel one is it doesn't have the fancy image features. So you lose the exclusive locking support, and you lose striping. Hopefully that will be coming in a Ceph release soon, or kernel release, I should say. Now, a problem when doing realistic testing with FiO is that you need something that resembles Postgres. We can and we do use pgbench. The problem is that pgbench workload and our real application workload differs quite a lot. Our real application workloads has a lot of very large transactions with very large objects where each row is a humongous beast, whereas pgbench deals with very well-formed transactions. So what we've done is we've observed the production I/O pattern, and we try to tune FIO to replicate the same pattern. And then once something provides good results on FIO, we apply it to a real database. And we have seen that if we see an increase of 25% on the FIO, our real-world database transaction rate will also be increased by about 25%. The important things you need to do is, first of all, allow the buffer cache. By default, FIO and most testing tools bypass the buffer cache in order to test your underlying storage. But hey, in production and in all real-world scenarios, you have a lot of buffer caches, so leave it on. Make the I/O depth 1, run multiple jobs, and use 8 kilobyte blocks, because this is what the database does. I would love it if the database used asynchronous I/O, if it used direct kernel interfaces, if it has a very deep I/O depth, but it doesn't. So you need to actually make your FIO parameters suck so that it replicates exactly what the database is doing. And that also means using fdatasync every 100th block or so, and use very, very large files, and use semi-random access. The reality is that even for read requests, it is often subsequent blocks, and it's often random. So you need to basically go in a pattern where it reads 2 or 3 subsequent blocks, then does a seek. So again, Postgres doesn't use any fancy I/O, so neither does the benchmark. Now, since I know that my read caches will actually cover up most of the reads, I focus mostly on write performance. I have 2 comparison targets. One is local software RAID 0 with 8 Samsung 850 Pros, 3 Samsung 850 Pros. For the writes here, the latency is fairly low, and the IOPS per job is also fairly low. And this is just a sanity check for how fast can it be if I just do some local hacking on just tossing together some hardware. I also have a full-on LSI MegaRAID RAID controller in RAID 6 with 24 drives. An interesting thing there is this one does a better job of the IOPS per job. It does have a battery backed write backup and so on and so forth. But if we compare the local RAID 0 with the controller-based RAID 6, if you look at the latency, the 99.99% mark on the RAID controller is measured in milliseconds, quite a lot of milliseconds. Now, our golden target, of course, is for KRBD to be beating these. And KRBD does beat the local RAID 0 in number of IOPS. It does not beat the local RAID 6 in number of IOPS. But the latency, which at the end of the day is what dominates transactions for us, it is much better than even the dedicated RAID controller. And unlike the dedicated RAID controller, KRBD does survive controller failure. Battery-backed caches are fantastic until the controller dies, and you now have data sitting in a cache that is battery-backed where the controller doesn't work anymore. This is when you start finding either your backups or you go look at your Postgres slave and figure out, was it up to date and can I fail over? Whereas on KRBD, we just start the same job somewhere else. So current challenges for us is, first of all, we have a little bit of a challenge around locking. If you run ext4 on RBD, and let's assume we have the following scenario. It's running, the database is running, and somebody reboots the switch. Either it lost power or it's maintained or something like this. At this point, a few minutes later, Aurora is going to detect that, hey, this compute node seems to be dead. Let me start the job somewhere else. So now your database is started somewhere else, it's happily relocated, and this new location mounts the RBD image and mounts the ext4 file system. Great, the database is now back up. And then the switch finishes rebooting. The all job, which is still running. Now, as soon as Aurora can talk to it, it will tell this node to, oops, please stop that job because I already started it. But there are going to be a few seconds where it runs, and it now happily remounts the RBD file system and writes to it. And if this happens, you're going to figure out how to repair a broken ext4 file system with a database on top of it. We thankfully tested all of these failure scenarios before we rolled it out to production, and I strongly recommend you test your failure scenarios in a lab before you roll it out to production. Based on this, we designed a workaround, which is a modified RBD wrapper. It literally unmapped us RBD lock add. Ceph does, and RBD does support explicit locking, but it's voluntary. Which means RBD map doesn't check the lock, but you can do so. Now, we try to lock the image, and if we don't get to lock the image, in other words, somebody else holds the lock, then we check the status of the image. If there's a watcher on the image, that means somebody else is holding the lock and they're still alive. In other words, whoever just told us to map this image is wrong, because the original job is definitely still running. We do check for the watcher 3 times, 15 seconds apart. And if we find it, we just say abort. If we get all the way here, then for the last 45 seconds, we haven't seen a watcher on this image. So we know that for the last 45 seconds, nothing has actually had this for RBD map, but the lock is still there. At this point, we blacklist the original lock holder and then steal the lock. On unmap, we remove the lock, and when the node is rebooted, it unblacklists itself. So this means that if we have one of these nodes and they go away for more than a minute or more than 45 seconds, and this is relocated, when that node comes back up, it's now blacklisted. If you reboot the node, it will unblacklist itself, because when a node comes back up fresh, it has no jobs. It will wait to be told what to do by the ROR master, so it has no mappings. We also need to make this faster. We beat legacy hardware for latency in the 99.9% range, but the problem is in the 50% latency mark and the 90% latency mark, we're actually beaten. But we don't want any compromise on performance. We are currently rolling out NVRAM for the Ceph write journals. It did take a little while to get that out there, because we have a requirement that all storage at rest must be encrypted. And if your RAM is non-volatile, then yes, it does count as storage. If it does arrive a complete power loss and it comes back in an intact state, then it is storage and it needs to be encrypted. PMC actually modified their NV16 to support encryption for us, so we're very happy with that. We do have single storage server testing, which actually looks awesome. The hardware is being installed this week. Some was installed yesterday, some today. One of the advantages of Ceph is we are doing this while the system is live, just taking down one rack at a time, installing the NVRAM, booting it back up. So we should have large-scale testing results in about 2 weeks. We are also experimenting with the Rocky V2, which is RDMA over UDP, in order to see if we can reduce some of the TCP latency. As soon as we have hard results for this, we're going to post it to the Ceph mailing list. If you want to try any of this out, if you can go to GitHub Common Medallia, you will find our modifications to both Docker and Aurora. And we're also going to put out our automatic provisioning there, this always network boot, the automatic BIOS updates, etc. That will be there as soon as we can take some things like the SSH keys out of the repository. We just need to move that into a separate repository, and then we're going to put that also out there as open source. If you want an exact replica of what we did, I'll share the slides. You can go look at it, but it's compute nodes, storage nodes, networking. This idea that everything is Linux, everything is something you just shell into, same storage tools for everything, and open source as much as possible for all of it. Thank you. If there are any questions, I'll be happy to answer them.
Excellent. Thank you. That was a great performance here. Everybody that's interested, I will be unmuting all. So if you would like to ask a question, you can unmute yourself in BlueJeans and ask a question, or you could just go ahead and type it in to the comment box. Any questions?
Maybe I should open this then.
Would you rather have hard no, or I would rather have a problem that's always a problem versus an intermittent problem that only happens.
And Thorvald, if you want to send me your slides when this is done, I will make sure that the video and the slides are posted for people that would like to go back and revisit this afterwards.
Absolutely. I heard some talking. I don't know if that was a question or not. It was very quiet.
No, I haven't seen a question come through yet. It's just a background noise after I unmuted microphone. So any questions going once, twice? Nope, here comes one. How do you handle OSPF updates for moving IPs around? Does the container run OSPF daemon, or does it talk to the switch daemon?
No, we run OSPF daemons on the host. So we treat servers and switches are all part of the same OSPF domain. The container does specifically not run OSPF. If it did, that would be a little bit of a security problem if anybody could reach into the container. But since it runs on the host, we run Quagga on the host. What Quagga sees is that, hey, there's a new kernel route to this 10.1.2.3.4. Let me put that into the OSPF domain and broadcast it. And same when the container goes away. Now Quagga will notice that, hey, the kernel route just changed, the 10.1.2.3.4 or 10.1.2.3, I can't reach it anymore, and puts that into the OSPF database, which is again propagated. Does that answer the question? Other questions?
Looks like sounds like your performance was feature complete. Everybody got everything they needed. So thank you very much. And remember, folks, next month we'll be back here on the 25th of February at the same time to hear about the latest and greatest from Cephfs. So
yeah, I'll be sure to be there for that one.
All right. And if you want to just keep an eye out on the mailing lists and social media and everything, I'll make sure to get the links to this YouTube recording and the slides that I'll post up on SlideShare after he sends them to me. So thank you very much, Thorvald. We really appreciate it. This was great.
Okay. Thank you.